Okay, I think now we are complete. Okay, welcome to the last lecture of this week, which will be given by Dr. Katsura on frustration-free models and field.
Okay, thanks. Thank you. And yeah, thanks for remaining here. Okay, so let me start my final, final lecture today, this week. And okay, so here's the outline of my entire lecture this week. And Wednesday and Thursday, yesterday, I was talking about frustration-free systems, but I was mostly focusing on the ground state physics. Today, I will generalize the idea of frustration-free systems to kind of excited state, and then I will discuss dynamics. And in particular, I'm going to focus on quantum many-body stars, which are some new class of weird quantum many-body states, and which are attracting recent interest in the dynamic in the context of quantum dynamics. All right. So, but in any case, this is the recap of frustration-free systems, which I was discussing in the past 2 days. And here is a universal form of the Hamiltonian, which is the sum of little hj, which is written as L dagger L. And because of this form, you see this is a positive semi-definite operator, meaning that any eigenvalue of h is non-negative. And if you find a zero energy state for this Hamiltonian, it should be a ground state because it's positive semi-definite. And this zero energy state psi saturates Anderson's bound, which means any hj annihilates this psi, right? And I took you through several important examples, like a ferromagnetic Heisenberg model, Legendre-Gauche model, for which the ground state looks like this. It's a dimer covering state. And I also introduced the AKFT model, for which the ground state looks like this. And this is, this model is a typical example of, representative of our symmetry protective topological spaces. And I also introduced the Kitaev story code in the first day. Yeah, go ahead.
That's a lot in this.
Is it?
Yeah.
But in any case, this kind of notion is limited to the ground state. We can only talk about the ground state from this kind of the Hamiltonian. But the question you might want to ask now is, can we generalize this kind of idea to excited state? And the answer is yes. And you can actually generalize this to so-called local divergence condition. And actually, the idea can be traced back to famous Baxter's paper about XYZ spin chain. This is a spin 1/2 spin chain. And here's the Hamiltonian, and it's a sum of little hj. And you see you have a xx, yy, and zz interaction. And this model is integrable by means of the Bethe, so you can write down the exact eigenstate in some form. But Actually, I think the paper is famous, but I have to say the paper is really hard to read because it's full of elliptic theta functions and it's rather intimidating. And I think the paper is famous, but I don't think many people have read it. But if you just look at some superstructure of the paper, what he was discussing is rather simple. And unlike the XXZ model for which Jx and Jy are the same, here you don't have UR symmetry, meaning you don't have a particle number conservation. So it's not really easy to do standard Bethe answers, right? Because, for the XXZ, you see all up state is an exact eigenstate, from which you can construct Bethe answer state. However, here, the first thing you have to figure out is what the difference state is. And actually, he found a different state, which is product state. It looks like this. And here, phi j is a two-dimensional complex vector, but it's not a uniform product state. These can be different. And this psi is not annihilated by local Hamiltonian. However, what he found was this product state psi satisfies this local divergence condition. So let me explain what it is. So if you act with a local Hamiltonian Hj on this side, then only, because this is a local Hamiltonian, only this part gets modified, right? The Hj, we modify this part, and then you get this difference of states. So here, on the first line, this will be Sj tensor phi j plus 1, but here you have phi j tensor Sj plus 1. And because of this form, you see, if you take a sum over these states, then you will just get 0. So this way, you can prove that this psi is a zero energy state of the Hamiltonian. And actually, the frustration-free case is just a particular case of this kind of relation, in which both S, J and Sj plus 1 are just 0. In which case you just get 0, right? But this is kind of more general. And the problem here is because this Hj is not necessarily positive semi-definite. This is not a ground state in general. And the question I want to address in the next page is if it's limited to product state or not. But before that, let me just show you.
Wait a second.
Yeah.
Could you please decipher what Sj is here? So phi j is some abstract product state, and then.
And Sj is also something abstract.
Okay, so so you demand that this vanishes, right, or what?
So you were demanding what?
You demand that this difference vanishes, right?
Yeah. So let me just show you some example. Yeah, some simple examples. That's what I want to show you. Okay. And yeah, you can just consider some simple example like L equals 3, just 3 side with periodic boundary conditions. So you just have a single triangle, right? And your size tensor product of phi 1, tensor phi 2, tensor phi 3. And if you act with H1 on side, then you get S1 tensor phi 2, tensor phi 3 minus phi 1 tensor S2 tensor phi 3.
H1 here is something that involves spins 1 and 2.
No, this is a single spin state, just a two-dimensional vector.
Yeah, but why the second spin got modified? I'm saying that H1 acts on spins 1 and 2.
Yeah. Exactly.
So it's rather H1. H1, 2 is, yeah.
It is more precise, to write it this way, but
okay.
Because in my lectures, I basically use this kind of notation. So, but anyway, so you're right. So it acts on two sides, 1 and 2. And then you can examine H2, right? And then you get H2 psi is plus phi 1 tensor S2 tensor phi 3 minus oh, see phi1 tensor phi2 tensor F3, right? According to that group.
Yep.
And then H3 psi is plus phi1 tensor phi2 tensor H3 minus S1 tensor phi2 tensor phi3.
So, a general question.
Yeah.
In the previous definition, definition of frustration free models, AJs are not the ones that act only on J's, like tensor part, tensor subspace, and LJs too. They can act on like different.
That's true. So in the beginning of my talk, I think I said HJ doesn't have to be local Hamiltonian. But here I'm considering a local Hamiltonian. Yeah, that's true. But anyway, so here I'm just considering this particular example XYZ, and then you see we have a cancellation between these two guys and these two guys and this guy and this guy. We cancel out, right? And this way we get H1 plus H2 plus H3 psi equals 0.
Okay, so this means that to construct such a state that is an eigenstate of H with zero energy, then we just demand that action of any, let's say, H1 on two neighboring spins gives this kind of anti-symmetric combination. Okay.
Yeah, actually, the actual calculation is quite involved because these guys are expressed in terms of elliptic data function, and we have to use some special properties of those elliptic data functions. So it's complicated. Yeah.
I'm sorry, but where do the coefficients Jx, Jy, Jz go?
Yeah. So as I said, I mean, linear calculation is more complicated. I mean, what you have to do first was you need to parameterize these Jx, Jy, and Jz in terms of elliptic functions. And this phi, I don't remember, but anyway, so this phi j is a two-component vector, but these components are expressed in terms of elliptic data functions, but I don't remember what it is. Maybe Tomas knows the answer, right?
Yeah, not by now.
We have to go to his papers.
The J's are inside the phi.
Sorry.
J's are inside the phis.
So you're right. So I think, I don't quite remember, but this is some function of, the first one component A4, I don't know, JP plus Q, something like that. So it really depends on J. So by J you mean side index, right?
No, I mean large J.
Jx, Jy, Jz. Yeah, that's true. So we first need to parameterize these Jx and Jy and Jz using I don't know, elliptic modulus, something like that. I mean, here you have three parameters, but overall factor is not so important. But you still need to introduce two parameters to parameterize these things, right?
Mm-hmm.
Yeah. Okay, and anyway, so the question I want to ask now is if it's limited to product state or not. And the answer is actually, you can generalize the idea to matrix product state. And this was actually done in the context of stochastic processes like asymmetric simple exclusion process, which is called ASAT for short. And this is not a quantum model, it's rather a classical stochastic process. So here we have to consider master equation, and this P double ket is a probability vector. And here, this is this P is a probability to have a particle configuration labeled by these sigma, sigma, blah, 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 sigma L, and each sigma takes 0 or 1. And 0 corresponds to empty site, and 1 corresponds to the presence of particle. And in this 1D system, this guy hops to the right with the transition rate 1 and hops to the left with the transition rate Q. And this M is called a transition rate matrix, but this is the sum of local transition rate matrices, and each guy looks like a 4x4 matrix, and this guy acts on the site J and J plus 1. You can think of this system as a effective spin 1/2 system. If you identify up spin with empty site and the down spin with the particle. And then Derrida and others found the steady state of this master equation in the form of a matrix product state. And here's the answer. And in this kind of business, the boundaries are really important, but let's forget about it. And if you look at the bulk part, you just have this uniform product of these vectors, but these E and D are not just numbers. They are matrices satisfying this kind of algebraic relation. And in many cases, these D and E matrices are infinite dimensional. So it's not so easy to write down these D and E. But in any case, what we really need is just this algebraic relation. And using this relation, we can show that this is zero eigenvector of this matrix M. And because you can show that this local product of ED, these vectors satisfy this relation. And you see, this is a something minus something. So this is a matrix product generalization of the local divergence condition. So, and okay, now let me prove it. And what we want to show now is this identity, m over 1 minus q, ed, tensor ed, equals this minus this. And the left-hand side is so this M is just a 4x4 matrix. It looks like this. So 0 q minus 1 minus q 1 0. And if we compute the tensor product here, actually the order is important. Because they are matrices, so ED is not equal to DE. But anyway, so you have EE, ED, DE, DD, right? And then if you compute this matrix vector product, then you get just 0 and QED minus DE. And for the third component, you have minus QED plus DE. And the last one is just 0, right? And now you can use that relation, this dE minus QED equal 1 minus Q D plus E. Yeah, this is often called a quadratic relation because you can reduce the quadratic thing to a linear one, right? And if you plug that in here, then you can just, this is minus the right-hand side of that equation, right? So you get minus D plus E. And this one is, yeah, this is exactly the same equation. So you get D plus E. Right? So next, let's compute the right-hand side of the first equation. So minus 1 tensor AD. And this is just minus E minus D ED, right? And the second one is ED tensor minus 1. So minus E minus D, right? And then if you compute the difference between them, then you get minus E plus E. So, and this is exactly the same as what I computed here. So this way you can prove that local divergence condition for ASIP. Okay? And this relation holds locally, right, for any pair of neighboring sites. So if you add them up, then you just get 0. Because of, we have a telescoping relation here. Okay, so now here's the outline of my today's lecture. And in the first part, I will give more physics motivation and introduction. And I will introduce the notion of eigenstate thermalization hypothesis, which is called ETH for short. And then there are several classes of systems for which the ETH will be violated. And one of the such systems is called a many-body skirt system, and this was motivated by a recent experiment on readable atom systems, and people often model such a system using the PXP model. And then I will review several previous results about quantum many-body skirts. And in the second and third part, I will take you through several different examples of models with quantum many-body skirts. Okay. Okay, so let me start with something quite fundamental. That is the foundation of statistical physics and thermodynamics. And as you know from your daily life experience, if you put an isolated system, and then this kind of isolated macroscopic system relaxes towards a steady state at late times, right? And here's one schematic example, and you're putting gas or particles inside this box, and initially the density on the left is high, but it's on the right is low, so you have a uniform density of gas here, but if you leave it for a while, and then at late time, as you can expect, you will get some uniform gas. And, that is what you learn from your daily life, right? But the question is, but the other way doesn't happen, right? But the question you might want to ask is why this kind of relaxation happens in macroscopic systems, either classical or quantum. And this kind of problem can be traced back to famous von Neumann's work in the 20s. And since then, people have been trying to understand why this kind of hierarchization happens. And then people came up with the idea to use the notion of typicality. And let me explain what the typicality is. And typicality states that a great majority of states with the same energy are indistinguishable by macroscopic observables like total energy, total particle number, or some density of particles or something like that. And here's a schematic picture of the Hilbert space. The energies are close to each other. And you see in these gray areas represent some exceptional states. For instance, this guy has no uniform density, and here you have a flow inside this box, right? In the rest of the white region, they are indistinguishable by any macroscopic observables. And the point here is that the number of states in the white region is much larger than the number of states in the gray region. So this is just an exaggeration, and in reality, these gray regions are too small to see. So the measure is 0. And if you introduce this notion, then you can naturally understand this kind of hierarchization phenomena. And because if you start with any exceptional state, and then if you evolve the system, then you are leaving this gray area, and then this guy is moving around in the white region. But the chance that this guy goes back to any of this gray region is quite small, right? It's measured 0. So this way you can understand the kind of the notion of the arrow of time here. And then you can understand that thermal equilibrium just means common properties shared by the majority of states in this white region. And you can also naturally understand why microcanonical ensemble works here. Because microcanonical ensemble just means that you are taking the average of some observable over the states which are close in energy, right? And if you take some average of some observable over these states, because the number of states in the white regions, is much larger than those in the gray region, so you just get the average over the states in the white region. That's why this kind of argument works, right? And you can also, as I said, you can also understand the summarization in this picture. And summarization is nothing but the approach to typical states from atypical states. But so far this is rather conceptual, but people have been trying to verify this kind of picture using experiments and numerics. And this is a famous experiment done for this kind of cold atom systems, which is well described by 1D Bose-Hubbard model. And initially, there are particles on every other side. But if you evolve the system by this Hamiltonian, and then at the end you get a uniform density. And this is a schematic picture, but here's the actual experimental result. And the vertical axis is the number of particles, probably not particle density for odd number size. And you see if you label the size like 1, 2, 3, 4 in this direction, and then initially there is no particle on the odd numbered size, but particles are only at even numbered size. So then this vertical axis, this one is 0 at time 0. it goes up like this, and then oscillates like this, and at the end, it goes to 1/2, and this corresponds to this picture, right? And people really confirm this kind of behavior experimentally, and it is consistent with numerical result, like time-dependent energy result. And okay, this is not an experimental result, but this is a numerical result. Rigo and others studied some many-body system, and this is a expectation value of some observable O in every energy eigenstate. And actually, the point here is if you increase the system size, then this expectation value versus energy curve falls into some smooth function. And you see this deviation goes to 0 if you increase the system size, and if you shrink this energy window. But anyway, so let me introduce the eigenspace normalization hypothesis more precisely. And here is our setup, and H is the Hamiltonian, and by E and K, I mean normalized energy eigenstate. And O is a microscopic observable, and by rho MC, I mean microcanonical ensemble. And the energy shell is a linear span of those energy eigenstates, whose energies are between E minus delta E and E. And okay, so here's a definition of thermal states, and a state E and K is said to be thermal if the expectation value of this microscopic observable in En is approaches to this microcanonical expectation value if you take a thermodynamic limit. And a strong ETH states that all these E and K in the energy shell are thermal. And this is believed to be true for a large class of non-integrable systems, but there is no proof. Conceptually, it was introduced by von Neumann and others, again and again in the history, and there are a lot of numerical evidence for strong ETH. And there is a weak version of ETH, which states that almost all E and K in the energy shell are thermal. And this was proved under certain conditions, like if you assume translational invariance or locality of interaction, you can prove. But it was not proved, in the most general setup. But anyway, so these are the definitions of strong and weak ETH. Yeah.
Almost all here stands for in the sense of measure, probability measure.
Yeah. Actually, this is a bit sloppy version of the definitions, and people often use more precise definitions. Like people like Stredonic uses, you can say more precisely, but then here is a bit sloppy version of the definition. But anyway, so there are several different systems that violate a strong version of ETH. And historically, the most famous one is integrable systems. Because in integrable systems, you have many conserved charges, so the dynamics is highly constrained. And in this case, the strong ETH is violated, but in many cases, weak ETH holds. And for instance, the example of integrable system is S equal 1/2 Heisenberg chain. And the other systems, many-body local system is another example in which strong ETH is violated, and the weak one is also violated here. And for instance, Heisenberg chain with random magnetic field is one example of system with MBL. Recently, people also discussed systems exhibiting Hilbert space fragmentation. And for this system, naively, if you just block diagonalize the Hamiltonian, using a local conserved charge, you only have these big blocks. However, in such a system, you have some non-local conserved charge. And because of such a non-local conserved charge, each block can be further divided into small pieces, and typically you have exponentially many number of small blocks inside each big block. And for this case, sometimes PTTH falls, but sometimes it doesn't. But today I want to focus on the fourth class of system, which is systems with quantum many-body scars. And for this case, strong ETH doesn't fall, but weak ETH falls. And these systems are non-integrable, but have scarred states which do not thermalize for an anomalously long time. And okay, and actually, I have to say, I was an amateur of scars, but I got interested in scarred system when I read this very nice article by Marcus Wu, which was on the Quantum magazine in 2019. And there was a kind of shocking animation. This is a web article, right? And here you see, what he was saying was scars are something like this. Here you have a popsicle, and this guy melts. But melt freezes again and again. But this kind of thing doesn't happen in real life, right? But what he was saying is scars are something like that. And he also wrote some other interesting articles, which this one I want to recommend you. And he was writing some article about the relation between 15 puzzle and Nagaoka ferromagnetism. Nagaoka ferromagnetism is one of the exact solutions of Hubbard model more than one dimension. But anyway, it has almost nothing to do with scars. And anyway, so today I'm going to focus on many-body scars, but in the 80s, people discussed one particle scars. So let me explain what it is. So, if you consider this kind of system, which is called the Nemo-Wick-Stadium, you can find some regular pattern for some eigenstates. And the Nemo-Wick-Stadium is made up of a square and half circles. So it's a square capped by half circles from left and right. And a generic eigenstate of one particle eigenstate of the Schrödinger equation in this system looks like this. You don't see any pattern here, right? But for some eigenstates, this is the 199th eigenstate, but this is the second one. And you see some pattern, right? So, and this was what this guy called one particle scars in quantum mechanics. And the point is, even in this kind of classically chaotic system, some energy eigenstate shows some regular pattern. And this is one particle scar, but today I'm going to discuss many body version of such scar states. And this kind of scar business was motivated by recent experiment on readable atom arrays. And readable atoms are atoms in which one of the electrons in an excited state is in an excited state with a very high principal quantum number n. So here, if we consider rubidium 87, in the ground state, the outermost electron is in 5s orbital. If you shine a laser, and then this guy will get excited to 70s orbital. So this guy will, get bigger like this, and you can, you can arrange these readable atoms in this one-dimensional fashion by using the optical tweezers, and you can get this kind of 1D array of readable atoms. And here by black dot, I mean excited state, readable state, but this white dot is a ground state. And if you shine a laser, then this guy will be excited, and then this guy will create a van der Waals type interaction. And because if its excited state is big, so you cannot excite adjacent ones. So because of this kind of potential created, so this configuration is not allowed. And this is sometimes called the read-about blockade. And then experimentally what people found was the following. So if you start with a special initial state called a Z2 state, for which you have a ground state and an excited state in this alternating way, and then you will see oscillation between these two states, Z2 and Z2 prime. And this oscillation is robust, it doesn't decay. I mean, it does decay, but it decays quite slowly. And here's the actual experimental data, and the vertical axis is the domain wall density, but this means the number of adjacent pairs of particles which are in the same state. So initially, there are no domain walls in either Z2 or Z2 prime, right? So the domain wall density is 0, but it goes up like this and then oscillates. But it's decaying, but it's decaying quite slowly. And this experimental result is consistent with the MPS-based numerical calculation. But if you start with some other generic state, then this oscillation decays quite rapidly.
How do the relaxation times of these states and generic states compare? I mean, what's the relation, like thousands or?
Yeah, good question, but today I don't have any figure, and I don't remember if they show any comparison in their paper. But in the next page, I'll show you some comparison between this kind of state and generic state. Yeah, just sorry.
But you can go along your presentation. Maybe I was hoping you had a.
Yeah, maybe we can discuss after the talk. Yeah,
Sorry,
I think I'm sure there are some papers where they discuss. They compare this kind of special state and generic state. Okay, so this the heuristic experimental system is a rather complicated to model, similar discussed, but people introduced a bit simplified model, which is called a PXP model. And here's the Hamiltonian of the PXP, and this P is a projection to the ground state. And this X leads to a resonance between the ground state and excited state. So if you act with this PXP on ground state here, ground state for these three consecutive sites, then you get this configuration and vice versa, right? And actually, this was introduced in 2018, but me and Rezanowski also introduced a bit more general model this year. But anyway, so let's see how this Hamiltonian acts on the four-side system. And in this case, as I said, we have a readable blockade constraint. So the dimension of the Hilbert space is 7 for this case, and this 7 is the sum of the third and fifth Fibonacci numbers. And you can actually draw a state graph starting from this ground state configuration here. Every atom is in the ground state. And if you act with this term on this state, then you can excite the first atom, right? And then you get this configuration. And if you act on the local term for this state, and then you get these different particle configurations. And then from this state graph, you can construct a Hamiltonian. And here's a rule. So if you have a line, this red line between the states, then you put 1. I mean, if you label the states like a 1, 2, 3, 4, blah, 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 and then, for instance, here, 1 and 2 are connected by this red line. So you have a 1 as a 1, 2 matrix element. And this way you can construct the matrix expression for the PXP Hamiltonian. And so now let's discuss the properties of this PXP model. And people studied several properties. For instance, the level statistics of the model obeys Wigner-Dyson distribution, meaning the model is non-integrable. And this is the vertical axis is the fidelity, which is the overlap between the initial state and the state at time t, and this is time t. And if you start with Z2 state, then you will see some revival at some particular time. And you also see this kind of revival of fidelity for these 3 states. And people also study the energy versus entanglement. And here's the result. So this is entanglement entropy, and this is the energy. I mean, you can compute entanglement entropy for each energy eigenstate. And typical energy eigenstate just obeys volume law, but you see for this model, you have a low entanglement state, which forms this kind of arc. And we have an anomaly low entanglement state at high energy, and which is not so typical. I mean, it doesn't happen in a generic system. And people also found an exact eigenstate with low entanglement entropy for this PXP model. Lee and Maturunich found an explicit expression for zero energy state with low entanglement for this model. And so far, there are so many different models for which people found exact or approximate scarce states. But today, I want to focus on the exact quantum many-body scarce. And there are several different examples, but I don't have time to go through all the examples. So now let's focus on the first one and the third one. Embedding method and Ising and XY-like models. And there are several recent reviews in which all these models are covered. So let's start with the embedding method. And this is a lot related to the frustration-free systems. And this is just a recap of the sandwich method, which I was discussing yesterday and Wednesday. And this is the frustration-free Hamiltonian, which is the sum of Lj, dagger Lj, and size zero energy state if it's annihilated by Lj or Oj. And by sandwiching this Cj, you can create a new Hamiltonian. And if this Cj is positive definite, then this original ground state remains the ground state for this new Hamiltonian. But even if this is not positive semi-definite, this size zero energy state of the new Hamiltonian. But the point is, if it's not positive definite, then this psi may not be a ground state of the new Hamiltonian, right? And this is the idea of Shiraishi-Mori embedding. And they consider a particular case of this kind of sandwiching where Lj and Lj dagger are projection operator. And as a demonstration, they consider the case where this P is a local Hamiltonian of the Majumdar-Gauss model, which I introduced the first day. And this is the numerical result, and the vertical axis is, I think, the expectation value of this P in every energy state, and this is energy over system size. And I mean, if you increase the system size, this value falls, shows some collapse, data collapse, and it goes to some inverse curve. But for this case, the ground state of the magenta gauge model becomes an outlier of this curve, and the ground state of the magenta gauge model is here. So it's far from this kind of curve, right? And next, let me review the spin 1 xy chain. And here's the Hamiltonian of the model, and you have a xxyy interaction, and this is z square interaction, and this is a spin 1 model, not a spin 1 half model. So this sj z square is not 1, something. And locally is a 3 by 3 matrix. And interestingly, you can introduce this kind of SU2 algebra here. And here, this j plus minus is the sum of this Sj plus minus square. But, this is not really a spin raising or lowering operator because, S plus square raises the spin twice, right? And the S minus square lowers the spin twice. So it's not a simple raising lowering operators. Nevertheless, they satisfy this kind of SU2 algebra. But this is not really useful here because they do not commute with the Hamiltonian. Nevertheless, if you act with this J plus on O minus state again and again, then you can construct exact eigenstates of this Hamiltonian. And because, this is an exact eigenstate of the first term, and because if you act with J plus on this state, then you never create zero kit. So this is also an eigenstate, simultaneous eigenstate of the second term. And this way, you can construct a tower of eigenstates for this non-integrable model. And this is an example of a scalar model. And this kind of algebra, which okay, this is an exact algebra, but they don't commute with the Hamiltonian. But they satisfy so-called restricted spectrum generating algebra. So, which means you have some nice commutation duration which hold only within some subspace of the Hilbert space. Okay, now let's move on to today's main subject. And I will, okay, so this is just a recapitulation of the quantum variable discussed. And QMVS are states such that they are non-thermal eigenstates of non-integrable Hamiltonians, and they have finite energy density, and they have, low entanglement entropy. Their entanglement entropy doesn't obey a volume law. And I will construct several examples of models with exact quantum manifold pairs. And in the first example, I will use Onsaga algebra, which is what Onsaga used to solve the 2D classical Eisen model in his famous paper. And if time allows, I will also show you some other examples. So, any questions so far?
Maybe a philosophical one. So you're interested in constructing states that relax anomalously low. Is there some notion of what anomalously low means?
Actually,
anomalously
in
slow.
the rest of my talk, I will focus on exact many QMVS, which just do not relax. They just show persistent oscillation.
Okay.
But in reality, if you take a more realistic model, you have something looks like scars, but they show some relaxation. It's not a perfect persistent oscillation.
What is the spectral density of such states? Is it finite, or is it approaches zero as you increase system size? Does it scale with system size in some way? In your examples?
Yes, in my example, it's always zero. And in some examples, people constructed exponentially many square-like states, but even in such a case, the ratio, I mean, between the dimension of the Hilbert space and the number of such states goes to 0. If you take the thermodynamic thinking. Yeah, and typically in my examples, the number of the square space grows linearly with the system size. Yeah.
And do I understand it correctly that, well, you said that in your examples, those will be perfectly oscillating solutions and they will do this forever, but how stable are those with respect to perturbations which break this exact construction? As you said, they will start to relax, but is there understanding that this is still going to be a slow relaxation? Why is it the case?
Yeah, good question. So actually, I mean, in the first example, I will introduce some kind of engineered disorder. So you can introduce some disorder, but it's not a true disorder. It's more like, I mean, fake disorder.
Very particular configuration.
Yeah, and for such a fake disorder, I mean, you still see persistent oscillation. But if you consider a generic perturbation, yeah, honestly speaking, I don't know the answer, but there is some papers by Alexei Motrunich and others, and I think they examine the stability of scars by perturbing the model, these exact models a little bit. And I think their conclusion was they are quite fragile. I mean, once you introduce tiny perturbation, they are gone.
Because I had the very same impression from the single particle example that this very weird state with some part, it seems quite specific to this particular geometry. If I change the contour of this billiards just by a little, it's going to...
Yeah, I think so. Okay. So, and I think the situation in the many body case should be more severe, right? I mean, the number of states grows exponentially with the system size.
Okay.
So the energy difference is quite tiny, right? Okay, so yeah, let's move on to the first example. And this story is based on the cooperation with my former students, Naoki Shibata and Yoshioka-san. And I first introduce my strategy, and then I will demonstrate how it works for perturbed S equal 1/2 xy chain, which is an integrable model. So you can perturb an integrable model a little bit and then construct a scarred model. And then I will discuss the properties of the model. And the essence is which you can find for S equal 1/2 case, but you can generalize this kind of model to have higher spin, spin 1, spin 3/2, and so on. And okay, so here's my strategy. And my starting point is an integrable model with conserved charges Q1, Q2, Q3, and so on. And by definition, they commute with integrable Hamiltonian H int. And then I will take a subalgebra of these conserved charges. And then the next thing I have to do is to find the difference eigenstate of H int. So this psi naught should be simple enough, like product state of MPS. And then, I find the tower of eigenstates generated by acting with those sublet algebra on this different state. And because they commute with the Hamiltonian, they have the same energy as psi naught, right? But so far, the model is just integrable model, so they have nothing to do with scars. But now you're adding some perturbation that break the integrability of H in. But they do not hurt the tower of space. And for instance, if you can find this H perturbation that annihilates these states, then this is, and if this perturbation breaks the integrability, then this is a desired perturbation which we are looking for. And for this Hamiltonian, new Hamiltonian, they can be thought of as scars. But so far, this is just a strategy, and now let me discuss a concrete example. Yeah.
But for step, I guess for step number 4, you need this. You need the eigenspace of this H integrable with the E0 energy to be grossly degenerate, because otherwise step 4 would yield all the same eigenstate, no?
But,
Because those are all conserved charges.
so, but you can spread the degeneracy by adding some trivial term like a magnetic field or particle number.
So that you take some integrable state for which there's just one. Okay, maybe I got it.
Yeah, I mean,
because you're saying that Q1 and etc. they all commute with the Hamiltonian essentially,
yeah.
right? So if you act on an eigenstate, you're gonna still have an eigenstate, unless it's grossly degenerate.
but you know, they can be further classified by the eigenvalues of some other, you know, conserved charge. For instance, the simple example is, you know, if you consider just a Heisenberg chain,
Yeah.
and you know, you can classify the eigenstates according to the eigenvalues of total SZ, right?
Yeah, right.
And yeah, if you add the magnetic field, then they have different energies, right? You can split the energies.
Yes, okay.
I mean, this zero is not that important, but for simplicity, it's easy to find kind of annihilator, right, in practice, but it can be, you know.
Because in the example you just presented, if I have a Heisenberg chain, indeed I can classify states according to the total spin, but then if I act on any of the states with a total spin, I won't get a different state. I need another operator, which does not commute with the Hamiltonian.
That's true.
That's basically what I'm asking. So you need not just the charges, but the lowering or raising operators for this charge in some sense. So it's not directly obvious how you're going to get them from Qs themselves in general.
You are worried about kind of non-abelian symmetry, right?
No, just with the example you gave. If you are given just the Heisenberg chain and this total SZ operator, then you have eigenstates of SZ, but then if you act with SZ on any of those states, you won't change it. So what you need is the conserved charges that do not commute with each other in some way. So xy and sx and sy total. Then you can get this tower, as you were saying, right?
Okay, now I got your point. So I see. So I mean, in some cases, even if you act with these charges, you don't create anything. That's what
yes, that's my point.
Yeah, that's true. And yeah,
So you need them to be
they have to be linearly independent with the origin. Yeah, that's true. Yeah, I agree. And in my concrete example, I'm going to introduce such operators.
Okay.
So, yeah. Okay. So now let's discuss a concrete example that is the S equal 1/2 xy chain. And here we have a L number of sides, and L should be even, and I impose periodic boundary conditions. And the Hamiltonian looks like this, and it's just a Sx plus Sy interaction. But if you use spin raising and lowering operators, you can rewrite it like this. And this, you can map it to free fermions via Jordan-Wigner transformation, which I introduced yesterday, and which was solved by Lipschutz-Mattis, and this is not me, but some other Katsura in the 60s. And that's because the model is integrable. You have many conserved charges, but the simple one is just a total SC, right? So, I mean, this Hamiltonian conserves the magnetization, but you can also find a bit more non-trivial conserved quantity, that is the bimagnum operator, Q plus minus, which is the sum of these guys. So this guy has momentum pi, right, because of the minus 1 to the j. And interestingly, this is an element of on-circular algebra, and you have infinitely many such. And yeah, this guy commutes with the Hamiltonian. And for this in Hamiltonian, this is one simple eigenstate, I mean, if you act with H int on this all down state, you just get 0, right? Because, you know, yeah.
I must have missed what Gonzalez algebra is.
Yeah, I'm going to explain to you later. But anyway, yeah, there's an interesting point here. You know, if you go to momentum space, this is just free forming, so you can diagonalize quite easily. But you know, conserved charges in real space is not so easy to figure out, right? But this is written in real space. That is an important point here. And so, so let me explain why it's called bi-Magnum operator. But before that, let me discuss just one Magnum state. And as I said, this all-down state is an eigenstate of this Hamiltonian. If you flip the spin at side j, this state is not an eigenstate of the Hamiltonian. However, I mean, if you act with the local Hamiltonian on this state, then you will move this up spin to the left or to the right, right? I mean, and the flip spin behaves like a particle. Now you can consider a block state of this kind of single flip state. And yeah, if you assume this kind of form, and then you can show that this is an exact eigenstate of the xy Hamiltonian, and you get this your familiar cosine band, right? But this is just a single Magnum state, but you can introduce something similar for two up spins. And this is the, I mean, by j plus 1, I mean state in which, I mean, the spins at side j and j plus 1 are up spins. And similar to this block state for a single spin, single magnum, you can also construct a block state for this kind of state. But in general, such a state is not an eigenstate of the Hamiltonian, xy Hamiltonian. However, if the momentum k is exactly pi, and then this state is an exact eigenstate of the Hamiltonian. And actually, this state is created by Q plus, right? So you can think of Q plus as a creation operator for a bi-Magnum state with momentum pi. And then, because Q plus commutes with the Hamiltonian, you can construct a tower of exact eigenstates of H int, right? But, I mean, there's an upper limit, so because this is 0. And it is more convenient to work with a coherent state of Q plus, and this is defined like this. This psi beta is a coherent state of Q plus. And yeah, you can also formally write it this kind of Taylor expansion of this state. But what is interesting here is that this coherent state can be written in this matrix product form. And so let's prove it. Yeah, this is actually an interesting exercise. So this Q plus is sum of these guys, right? And then this psi beta is beta square Q plus all down, but you can write it as down. And then, because S plus square is 0. So yeah, it looks complicated, but you can avoid using exponential and just get this, right? So 1 plus, when j equal 1, this is just plus 1, so you have 1 plus beta square is 1 plus s2 plus 1 minus beta square s2 plus is 3 plus blah, 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 1 minus beta square is L minus 1 plus is L plus, and they act on all down. And then, this is a scalar, but you can think of it as a product of row and column vectors, like 1 beta S1 plus, 1 beta S2 plus, and so. And then you can combine this column vector and row vector here, and then you can make a 2 by 2 matrix, right? And they have to go down. And then you get 1 minus beta and because S2 plus square is 0, so you just get 0. And in the next one you have 1 plus beta yeah, something like this. Yeah, we have to work out a bit about the boundaries, but anyway, so you can write it in the form of the matrix product, and finally you get like this. And this way you can prove that this coherent state becomes a matrix product state. And the next thing I want to discuss is this state satisfies this telescoping relation. And this is a local Hamiltonian of the xy chain. And if you act with Hj on the matrices here, Mj and Mj plus 1, and then you get something minus something, and this Lj is this 2 by 2 matrix. Okay, now let's prove it. So here you can write it like this, right? Trace M1, Mj, Mj plus 1, and Mj is a 2 by 2 matrix with this state component. Now let's apply local Hamiltonian Hj on mj plus 1, and then you get this, this is sj plus 1 minus plus sj minus sj plus 1 plus. So you get and yeah, if you act with sj plus on mj, then you know they will be 0, right? Because s plus up is 0, so you can just raise this down to up, and then you get up j 0 0, and here you have yeah, so you are lowering the spin. So this is just goes to 0, and you get j plus 2 theta. And from the second term, we have something different. So from this, you get 0. And this one just up. Right. And yeah, I don't think I have enough time to write everything, but anyway, so if you compute this sum, you get 0. Yeah. Yeah, this kind of diagonal matrix. And then you can compute the right-hand side of the derivation. Here J is 1, right? And this is minus. Yeah, this is the right-hand side of the derivation, and actually most of the terms are just 0. So from the first term we get just 0 0 beta down up 0 minus. From the second one you get 0 minus 1 to the j plus 2 beta up down 0 0. So yeah, then this is the same as this one, right?
Matches up to the sign of the upper right term.
Yeah, yeah. Oh, I see. So there's some mistake. Yeah. So yeah. So this should be 2. This should be 1.
Yeah.
And then
Now
then
it should be fine. Yes.
this is 1. But because of the minus sign here, so we get the same answer. So, yeah, here's fine. So, in this way, you can prove that this H int, xy Hamiltonian annihilates this coherent state. And because the Hamiltonian conserves, it has Euler symmetry, every state with fixed SD is also zero energy state of the H int. So actually, interestingly, even if you don't know anything about integrability or on-site algebra, but just using this telescoping trick, you can prove that these are eigenstates of the Hamiltonian. Now, but so far I've been just talking about integrable xy model, so it has nothing to do with scars. So now let's perturb it to make it non-integrable. And so we need to find a designed perturbation such that H part annihilates this psi beta, and it breaks the integrability of the original Hamiltonian. And now, to find such a design perturbation, let's look at the local structure of the MPS. So this psi beta is a coherent state of Q plus, right? And I have written down the first 3 matrices here. And if you really compute this product, then you get this 2 by 2 matrix with these state components. And if you carefully look at these guys, then you will notice that there are no these states, down, up, down, and linear combination of these two. They never appear in this matrix. And that means if you consider projection to any combination of these two guys, it will annihilate the psi beta. So here's a possible perturbation. The first one is a projection to this guy, and the second one is a projection to this thing. And you can also consider hybridization between these two. And interestingly, these coefficients can be made random. They can be any number, right? Yeah.
How do we know that this breaks integrability?
Yeah, that's what I in the next slide. So yeah, just a second, please. Anyway, so this way, but naively, if they are random, there is no chance to expect integrability, right? But of course, we have to check it numerically. And that's what I'm doing here. So let's check if it's integrable or not. And the standard diagnosis here is the Weber spacing statistics. So consider this perturbed Hamiltonian, and I arrange the energy levels in this increasing order, and this delta EI is the level space spacing. And you can introduce this mean level spacing, and we can talk about this average. And then if the Hamiltonian is integrable, and then this level spacing distribution follows the Poisson distribution, but if it's non-integrable, then this will follow Wigner-Dyson distribution. And here's the numerical result, and I have studied the 16-site system and only at the diagonal perturbations. I didn't add the hybridization term. And this is the result for zero magnetization sector, and you see this P of S beautifully follows the Wigner-Dyson distribution, so which suggests that the model is non-integrable.
Does this hold for any kind of non-integrable model?
You mean this one, right?
Yes.
I mean, so I think so. I don't know. Maybe Tomasz has some opinion. I don't know. I mean, if it's non-integrable, I think it's okay, but you know, but I don't know, I don't quite remember, but there is some weird example, like a Richardson-Gordon model, which is integrable, but whose level statistics is very weird. Is that true?
Yeah, there are models with linear statistics, but if it's linear Dyson, it's almost sure.
Okay, yeah. For this, it's okay. In some integrable model, they show something different from Poisson. So yeah, so if you trust me, then it's non-integrable. And you can also study the entanglement entropy of this model, and this is just the definition of half-chain entanglement entropy. So you can just divide a 1D system into A and B subsystems with the same system size L over 2, and this is the definition of the reduced density matrix for subsystem A. And from the entanglement entropy is just the von Neumann entropy of row A. And there is some argument that you can think of this entanglement entropy as some dynamic entropy of a subsystem. And if this entanglement entropy obeys a volume law, then the state is thermal, and if it obeys some volume law, then it's non-thermal, athermal state. And here's the result for my model. And if you add random perturbations, most of the states just follow the volume law scaling. But these special quantum many-body sparse states are far below this curve, and they have small entanglement entropy, and the entanglement entropy obey sub-volume law. And you can actually, these are the corresponding states, and you can actually prove that their entanglement entropy is bounded about by logarithm of system size L. And this is a rigorous bound. And you can also study the dynamics of the system. And it's a bit artificial, but let's consider coherent state as an initial state. And then if you evolve this state with this Hamiltonian H, this non-integrable Hamiltonian, because this H perturbation just annihilates this state. It doesn't do anything here. So you can really write down the state at any time. And you see from this divisor of the state happens at T equal Tk, which is a multiple of pi over H. H is the magnetic field strength. And here's the numerical results for L equal 10 and H equal 1.0, and these are some random numbers. And this is the fidelity, and the vertical axis is fidelity, this is time. And if you start with the coherent states, then they show this kind of perfect divisor, perfect oscillation of the fidelity. If you start with this kind of product state, 1010, or some random initial state, it decays rapidly like this. And here's entanglement entropy. This is entanglement entropy. And if you start with the coherent state, it doesn't change. It's just constant in time. But if you start with this product state or generic state, then it grows up like this. And then it goes to the page value. And I think it's almost the time, but let me just comment on the relation to the on-site algebra. And actually, this looks a bit different from the XY Hamiltonian, which I wrote before, but it's unitarily equivalent to the XY Hamiltonian. But it's more convenient to use this one here. And this guy commutes with this Q and Q hat. And, the sum of them is just a quantum eigen Hamiltonian, right? And interestingly, this Q and Q hat obey this interesting algebra, Durand-Rayleigh iteration, and you can actually further decompose Q hat into 3 parts, Q1 0, Q1 plus, and Q1 minus, and you can show that each of them communes with XY Hamiltonian. And this Q1 plus is more or less the same as Q plus, which I discussed so far. And actually, any polynomial in Q and Q hat commutes with this Hamiltonian, and you can construct something more complicated which still commutes with the Hamiltonian. And this is the one example, Qm plus. So here you are sandwiching this string of Sz by S plus on the left and the right. And using this kind of more complicated operators, you can construct scarred model with longer range interactions. And you can also construct higher spin models. And yesterday I introduced these Tauent's, clock and shift matrices. Using these matrices, you can construct Potts-like model, and this is the Hamiltonian, and it's complicated, but you have tau and S here, S plus minus here, and when n equals 2, this Hamiltonian reduces to the XY Hamiltonian. But n equals 3, it cannot be reduced to any free-forming Hamiltonian, but it's still integrable. It's truly interacting model, so it's a non-free-forming model. This model has U1 symmetry and self-duality, which means the model is invariant at the free form sigma and tau matrices. And what is important here is this model has also the algebra symmetry. So this Q plus commutes with the Hamiltonian. And this Q plus, you can also, using this Q plus, you can construct higher spin version of the squared models. And so let's consider the S equal 1 case, and this is our starting point of the integrable Hamiltonian. And it's complicated, but anyway, you can show that this guy commutes with the Q plus. And then you can write down the coherent state of Q plus. And again, this is a matrix product state, but here the bond dimension is 3. And by looking at the local structure of this MPS, you can find desired perturbation that breaks the integrability, but it doesn't hurt the towers of scarce states. And these are entropy and fidelity, but you see you have arc of scarce states here. And I don't think I have time to go through the final part, but anyway, so I introduced some different methods to construct some models with exact scars. Let me skip them. This part is kind of relevant to experiments. Together with the experimenters, this Tomita-san is called as an experimentalist, and we didn't really do any experiment in this paper, but we proposed some experimental system which hosts scarce states. But anyway, so let me skip it here. And okay, so here's the summary of my final lecture. And I have introduced the notion of local divergence condition, which is a generalization of the frustration freeness. And using this kind of idea, I have constructed a model with scars, which is a kind of non-integrable deformation of S equal 1/2 XY spin chain, and you can also construct higher spin version of the model. And I didn't have time to discuss other examples, but let me stop here. So, yeah, thank you for your attention.
Yeah, I will pretty briefly outline what the useless.
Okay, okay. So yeah, the idea is simple. So this is just the integrable Hamiltonian, and this Hj is a local Hamiltonian density, and you can construct a boost operator. Here you have J site index here, and by commuting B with a conserved charge, you can generate higher conserved charges. And for instance, for S equal 1/2 Heisenberg chain is a typical example of an integrable system. And if you commute B with H in, then you get Q3, which is proportional to this sum of scalars in chirality. And the integrable boundary state is a state such that it's annihilated by all the odd parity conserved charges. And here, parity operation means just inversion in this 1D system. And if this is odd parity operator, chain flips the sign when you sandwich, this Q by I, right? IQI goes to minus Q when it's odd parity operator. And this is a lattice version of the boundary state discussed in integrable quantum field theories. And then, but anyway, so some of these conserved charges are still just some integrable model, right? You have infinitely many conserved charges. But you can break the integrability of this guy by adding some non-integrable Hamiltonian here. This H naught is some non-integrable Hamiltonian. And for instance, you can show that the ground state of the Magenta-Gauche model is an integrable state of the Heisenberg model. I mean, the models are different, but the ground state of this guy is annihilated by all the odd parity conserved charges. But that means, this state is still an eigenstate of the sum of Magenta-Gauche Hamiltonian and these conserved charges. And because we already added this term, so it's no longer integrable. And you can also check the non-integrability by just checking the river statistics.
No questions. Thank Hosho for the presentation. Thank you.
Yeah, no problem.
I have to run now.
Yeah, I have next week.
Enjoy your